Hello, everyone. My name is Katie Emilio, and I'm an engineer in the Professional Development Department at ACI. I'd like to welcome you to today's webinar, Understanding the ACI 56221 Concrete Repair Code webinar series, Part 1. We're very glad that you could join us. Today's presentation has been approved by AIA and ICC for 2 learning units. Our webinar today will discuss the background for the need of a repair of a concrete code. And the learning objectives are as shown on your screen as well as in your handout. And now I would like to take a moment to introduce our speaker for today. Keith Kestner, a fellow of ACI, is a project director with Simpson, Gumpertz & Heger, Inc. Keith is a structural engineer with over 25 years of professional experience in the evaluation of existing structures with specialized experience in non-destructive testing, concrete corrosion damage evaluation, and the development of structural repair solutions. He currently serves as a member of TAC, CSAO, and ACI Technical Committees 562, 318C, 364, and 228. He also serves as a trustee of the ACI Foundation. He has received several awards from ACI for his work in code development and adoption. He's a registered professional engineer in several states and a registered structural engineer in Illinois and Hawaii. He received his PhD and master's degrees from Cornell University and his bachelor's degree from the University of Connecticut. And now I'll pass the screen to Keith to begin today's presentation.
Thanks, Katie. Thanks for the introduction. Thanks everybody for attending. I guess welcome to the webinar. Very excited to go through this material with you today. And as we get started, I'd really like to thank Khaled Nalawi for all of his help in organizing the slides and developing the materials for this webinar, as well as my co-presenters. This is first part of a 4-part series. So my co-presenters include Mike Bartlett, who's speaking tomorrow, David Tepke, and Kyle Stanish, who are both speaking next week. And I guess as Katie mentioned, if you can watch these live or you can watch them on demand. So as the webinar materials, as you can see on the screen, we're talking about the ACI 56221 code, as well as the guide to the ACI 562 code, which is a joint document that was developed by ACI and ICRI, and of course the slide handouts. Another piece of information that was developed to support ACI 562 is a series of articles on concrete repair and how to use the ACI 562 code. There's 11 parts to it. And if anyone's interested, send myself or Katie or Khaled Nalawi an email and we'll get a PDF of those articles to you. As just some overall objectives of this seminar series, we're going to talk about the ACI 562 code, learn what really a design basis code is, as that's really how we're establishing the specific requirements for a concrete repair project. We'll talk about the load combination strength reduction factors that are used in ACI 562. It's a lot of what Mike Bartlett's going to talk about tomorrow. Test methods that can be used for assessment, and the different types of strengthening mechanisms that can be used for concrete structures. And finally, the importance of quality assurance and quality control. As you recognize, a lot of our concrete repair problems start with a lack of quality assurance, quality control during original construction. So let's talk about some methods that can be used to ensure that we get our repairs right. So just as an overall outline, I'm going to focus a lot about the need for a concrete repair code. And some of our talk about how the concrete repair methods and different things are being used and what sort of successes that we've had. On the next slide, we'll talk about the chapters in ACI 562 and how they're put together. And finally, throughout the presentation, we'll have different examples of different types of repairs that are being completed. This program is separated into 4 different modules. There's 10 of them total that'll be gone through in the 4 parts of the seminar series. They're going to do 3 of them today, hopefully, as long as time works out. The overall outline for the modules is shown on the screen. We're going to talk about the history of repair codes, I know nobody was expecting a history lecture, but it's actually interesting how we came to this point. Talk about general requirements and some criteria when using those codes. And then finally, in some of the other modules, we'll talk about preliminary assessment, preliminary evaluation, when that needs to be performed, what material properties will be used during the assessment, what design strength equations, strength reduction factors apply when you're evaluating a structure, and then a key thing, how to ensure the durability of a repair. We're repairing a structure because it's been a problem. So how do we prevent the problems from occurring in the future? And how do we not just ensure that the repairs are durable, but the repaired structure is durable? And then the last module goes through some real life examples. These are taken from the ACI ICRI guide that will talk about how some of these code requirements are put into practice. So getting into this is our first module. This is the evolution of concrete repair history, and let's get into it a little bit. So to start, we're talking about the use of concrete, and this is always a cool fact to me because concrete's the second most consumed substance in the world. That's so, except for water. So we use more concrete than we do asphalt, more concrete than steel, more concrete than timber. Except for water, and you put a lot of water into concrete, as most people know. It's the most commonly used material on Earth in terms of construction. How many tons of cement is produced every year? In the US, 86 million tons. That's just the cement. Worldwide, 4,100 million tons, and those are 2018 stats. Everything's gone up since then. And talking about the use of concrete, how big is our concrete industry? US, we're producing about 10 billion tons of concrete every year. It's a $37 billion industry, and it directly employs over 10,000 workers. So it's a huge industry in the United States. The commonly heard stat, and I'm not convinced it's correct, but it's commonly heard. Basically, every person in the United States, there's 1 cubic yard per year of concrete that's produced just associated with you. Give you an idea of how much concrete is being produced. And the nice thing about concrete, if we're careful with it, we maintain it, we keep it dry, we keep it happy. How long is it going to last? Thousands of years. And we go back to things like the Pantheon in Greece, some of the aqueducts in Rome. They've been around for thousands of years. There's not too many things that have lasted that long. So what are advantages of using concrete? And this is like the really cool part when you're a little kid and you start to see that you can make all sorts of shapes out of it. It's fire, weather resistant, and it can be extremely durable. So why do structures need repair or strengthening? What happened? Why are we in this problem? There's always a situation where things can get overloaded. You know, as a kid, I used to play with the Legos, and I would always end up breaking my Lego bridges, and you can see a broken bridge on there. You can have deterioration as a result of corrosion, other types of damage, inappropriate materials. You can have defects, inappropriate materials, bad choice of materials, not strong enough, design and construction errors. So repair or strengthening or both may be needed to come from a design error. Let's just say during construction, the contract doesn't follow the specifications, or the specifications were incorrect. We got some of the wrong material. Maybe it wasn't sufficiently durable. We also may have to assess the capacity of a structure to accommodate larger loads or determine the feasibility of changing a structure. We have an existing structure, we want to expand it. There's new loads, new lateral forces, new gravity loads. And then finally, to evaluate structures from accidental effects, such as something that may occur from a fire or a flood, foundation settlement, overloads. So there are a lot of different reasons why we may need to evaluate an existing structure and then repair or strengthen it, or both. Okay, the other situation we get into is the effect of the environment. Long term, we know chlorides can cause deterioration, that can cause corrosion damage. Change in use, code upgrades. We know in certain situations, due to certain conditions being identified, A building code will require existing structures to be strengthened, maybe for seismic reasons, maybe for change in use. We're going to put a new use in a structure. We're going to add classrooms to a residential structure. So those are all types of things that may cause a need for repair or strengthening of both. And one of the important things to recognize, and this is difficult because most of us as undergraduates and graduate students, we learn about design of new structures. And there's actually very few people that take coursework in existing structures. And new structures, just like in class, there's a clear standard of practice. The owner, the design professional, they really just follow the code to create a new structure. And it's for a building code official, if there's any building code officials on the presentation today, their job is relative, I'm not gonna say it's simple, they have the hardest job of all, but to enforce the code. And the code itself for new construction is relatively clear. Now for an existing structure, and we'll get into this, what is the standard of practice? What should the code requirements be? For an owner design professional, the owner has to always maintain the structure in a safe manner. That's pretty well established. But once we get into repairs, outside of some clear code guidance, a lot of stuff, the extent of work that's required, is negotiated unless there's some clear requirements to do otherwise. I mentioned standard of practice. This is a common term that's thrown about, and it really goes back to the origin of it. It really goes back to English common law, where it was kind of established that the public has a right to reasonable care to be excised when we're charging people for services. If you go to get a haircut, you expect to get a good haircut. But it's really been established that the standard of practice, the degree of care that professionals under ordinary circumstances would use for similar projects. It's not the absolute best. It's not an unreasonable. It's the ordinary care. So typical practice. Code standards guidelines help define the standard of care, and some documents that you may be interested in are shown on the screen. ACI 132 recently published responsibility in concrete and rehabilitation construction that discusses the standard of care for concrete rehabilitation projects. And there's an ACI SP, which also discussed a similar topic, which is shown on the screen. So we start talking about the repair industry and how big it is. We talked about how big the concrete industry, but the repair industry itself in the US, we're spending $18 to $21 billion is estimated by the American Concrete Foundation, or $30 to $35 billion per year. That's spending on concrete repairs of existing structures. And you can see some of the projects that Jefferson, going from left to right, the Jefferson Davis Memorial in Kentucky, some silo repairs, and then a deteriorated stadium. So some of the types of projects that people get involved with. Some of the factors affecting concrete, why is concrete deteriorating? We know that new construction, it will typically take a relatively long time if it's built properly before it'll deteriorate. But what about repair structure? How long will a typical repair structure last? To look at that, two different groups. One was the US Army Corps of Engineers. The other one was done in England, which was done by the Building Research Establishment, the BRE. Looked at that situation, and they were performed over a period of 25 years. And they published in the late 70s into the early 80s. And they studied the repairs on more than 200 structures. And what they found was that the repaired structures, cause of deterioration was evaluated and documented, and lots of different types of deterioration was observed in the repair structures. Very commonly, corrosion, freeze-thaw, frost damage, excessive cracking, alkalized aggregate reactivity issues, just ordinary uncertain types of concrete deterioration, poor construction, and then other factors. So they were recorded under both. Deteriorated structures were repaired following the best practices at the time in the European study, and were performed by conventional methods conventional approaches, simple surface repairs, coatings, crack injections, see the different types of surface. And when they put the results all together, what they found was that these are the results from the United Kingdom. Most repairs, by the time you got to about 6 to 10 years of age, 70% of them had failed. About 20% only lasted less than 5 years and less. And very few repairs actually got to the point where 90% of the repairs lasted in the 11 to 25 year range. So really, if we start thinking about these repairs, most of our repaired structures are actually deteriorating relatively quickly. So what are we spending money on? We're repairing a repair. And you know, everybody knows that's one of the most frustrating things in the world when you keep doing things wrong and you do it again and again. So this information really caused the repair industry to step back and start thinking about this and what can we do better. And when they looked at what was the cause of the failed repairs, they found two main categories. Engineering, incorrect diagnoses, which was basically the LDP not recognizing the actual reason for the concrete deterioration. The repair design approach was faulty to start with. So consequently, if you start with the bad concept, you end up with a bad repair, and the shortcomings in the bad repair then manifested itself separately or in combination. There was inappropriate materials used to fix some of these structures. The next huge issue, obviously, construction issues, non-standard designs, non-conformance to design intent, accelerated construction where you sacrifice quality for speed for quality, improper application, the contractor not following the manufacturer's printed instructions. So therefore the material itself was never installed properly and was kind of doomed to failure. Improper workmanship, and the person executing the work didn't have the proper training to do it. Incorrect application of the repair materials, and local materials varying in quality. And then finally, insufficient funds where we just didn't put in enough money to actually get it done. So stepping back a little bit, thinking about this as a module on repair history, an ACI first published a concrete building code in 1910. So I took a look back through the ACI database to find the first paper that addresses repair. And it was actually published in 1926 by B.C. Collier, A Repair of Faulty Construction. It's 1.5 pages long, but the most interesting thing was the reason cited for concrete failure. It is found that they come under 3 headings. Excess mixing water. Too much water added to the concrete results in poor strength. We all know that. Bad aggregate. Aggregate wasn't durable. And generally improper design of the structure itself. So from 1926 to 87 years later, ACI published its first concrete repair code. So we've been dealing with this issue of concrete repair for a long time. So let's talk about how it's been addressed in some of the codes. The first building codes in the US, 1927 UBC, the Southern or the Standard Building Code, 1946, and then the BOCA, Building Official Code Administrators Code, 1950. And depending upon where you were in the country, you use one of these 3 codes. And the general concept in repair, when we're talking about this, and this is all pre-1980s, the repair philosophy was that if the anticipated value of the repair was less than 25% of the building, then an in-kind repair was typically allowed. So basically, if there was a low cost to the repairs, just put it back the way it was. 20 to 50% of the building value, unaffected portions of the building did not have to be upgraded to meet new construction rules, but the affected portions did. And then finally, if it exceeded 50% of the building value, then the building needs to be upgraded to new construction requirements. So there's some obvious issues with this system. People gaming the system to do costs, adjust the cost to make sure they don't have to strengthen or upgrade code to current code requirements. And The other situation would be what time period is that being done in? Is it 25% of the building value per year? So stretching out programs to adapt to different situations. So in the 1980s, there's sort of been a change in philosophy, and a lot of that was deemed that these cost model methods were considered a obstacle to the reuse of existing structures. That was discussed in a paper by Matera in 2006. So they got basically those cost triggers were basically pushed out of the building codes, and sort of this philosophy change became leave undamaged, unaffected elements alone, and apply new construction was only to things that are actually damaged. But then we started thinking about at this time frame a need for a material-specific repair code. In this time frame, and starting in the 80s, there's been a huge explosion in the concrete repair industry. A lot of what we're dealing with is the 1950s decision to have clean roads, so we had a lot more de-icing salts being used. All that de-icing salts being tracked into parking structures, causing damaged parking structures. There's a lot of improvements in repair materials, better improved design practices, installation, contracting, QA. All these things have been floating around for the last 30 years. So it kind of hints at a need for a material-specific repair code. A couple of other things that happened in the building code industry. In 1994, the BOCA, the IBC, and the SBCCI, they decided to create a single model code. They formed the International Code Council, which was published their first building code in 2000. And now it basically took all those three building codes and made one standard building code, which is actually a huge simplification in US practice if you're practicing in multiple states. They also created the International Existing Building Code, and now it's based upon the existing building code provisions in those three documents. And the intent of that was to provide flexibility, permit alternative approaches to achieve compliance with minimal requirements to safeguard the public health and safety and welfare, insofar as they were affected by repair of existing structures. So now we're in the 21st century. We have the International Existing Building Code. We have these are all called the I codes, and they reference other ACI codes and standards. ACI codes and standards then get referenced in the IBC, ASTM, all these other standards are all now referenced into the I codes. And really what we're focused on in the repair industry is the IEBC, and the intent of it is to safeguard the public health, safety, welfare, insofar as they're affected by repair, alteration, additions, change of occupancy of existing buildings. So those are the topics that are addressed in the IEBC. There's a couple different methods that you can use in the IEBC, and there's also some provisions in there for relocated and worked on historic buildings. And really the intent of the ICC is to create a complete building safety system. So one of the things the ICC does is things like the ICC evaluation service, which basically is intended to provide a pathway for new products to be used. New construction materials, things like FRP, have all been tested through the ICC evaluation service. Those are things that have been tested, but until recently had not been part of things like ACI 318 or ACI 562. So that provides a pathway for some new materials to get into the building codes. So now stepping back a little bit, with all those changes in the building code, why do we need a concrete specific, material specific repair code? And really it comes down to when we start to look at the IEBC, that has some very specific guidelines in it, but it's not specific with respect to material performance or how to assess or strengthen these things. So what do we want to do is really create a uniform set of requirements for repair of concrete structures. Consistent methods to decide governing code, consistent methods on assessing damage, while maintaining this concept of flexibility and repair solutions. So it's so ACI 562, one of the things we did is really have an integrated a lot of performance-based and some prescriptive methods. One of the things we clearly most distinctly did not want to do was to eliminate or take away the design professional's flexibility in repairing structures. Wanted to keep that as much as possible. As much as possible, we wanted this performance-based thing. So now as we start into Module 2, we'll start talking about the general requirements of ACI 562 and really taking us through this concept of preliminary evaluation that's present in ACI 562. So we talked earlier, IABC is the model code for existing buildings, and that's used in most of the US states. And this is the map that is shown is from the ICC website. And it's a little bit somewhat misleading. Some states, as you probably know, have statewide building codes. Other states' building codes are adopted locally. So, and this state indicates where at least one jurisdiction, the map indicates where at least one jurisdiction in the state has adopted the IABC. So what the IABC is doing is providing the minimum legal requirements for existing structures. But a limitation of it is there's nothing material specific, nothing concrete specific in the IABC. So one of the critical things that we've been working on at ACI was to get the IABC to reference ACI 562, to bring it in. And in the 2024 edition, it will reference it. And it'll say, as shown on the screen, repair of structural concrete shall be permitted to comply with ACI 562 section 1.7, except where some other things happen. And section 1.7 is the section of ACI 562 that specifically describes how you will use IABC when you're working with, use ACI 562 when you're working with an existing building code. Section 1.8 is appropriate when you're when there is no existing building code. Okay, so ACI 562 as a repair code can both function to supplement the IABC or standalone as a standalone code. Why is a standalone code? We're typically talking about building structures, but there's an awful lot of structures that are, we'll call them building-like structures. They may be industrial facilities, they may be piers or wharfs, they may be large silos. Those are typically not considered building structures, but the provisions of ACI 562 will work when you're repairing that type of structure. So you can use ACI 562 with the IABC. If you have a local existing building code, you can use it, or as I just mentioned, a standalone code. So talking about some general requirements, even when there is no existing building code, what is ACI 562? It provides a standard. It provides a standard, I mean, it's something that supports a standard of practice. And it still serves as a tool for an owner in the LWP. And when should an owner be looking for professional help? When a structure, a portion of a structure has damage, inconsistent behavior, structural deficiency, deterioration. Those are situations when this owner may want to seek out a design professional for repair. And if the repair is being done in accordance with the standard, that's certainly going to help us when we go to get approval of the repair plans from the building code official. So when is ACI 562 applicable? It's really intended for buildings that are actually complete, hold a legal certificate of occupancy. If the building's not complete or it doesn't have a legal certificate of occupancy, you really should be using the provisions of ACI 318. That's the new building code. So what type of code is it? I mentioned earlier, it's performance and prescriptive. New design codes are predominantly prescriptive. Repair codes are a little bit of a different animal. You got to have some performance-based requirements, and that's to give us that flexibility that we talked about. So it provides minimum material and design requirements for evaluation, repair, and rehabilitation of existing structural concrete, and it provides minimum life safety and performance for repaired concrete buildings. So it's providing these minimum requirements. So what is it doing? It helps the standard in industry practice, and that's critical. Until recently, engineers and contractors undertaking this type of work did so without the standard, without the benefit of a concrete repair standard. As a result, practices and materials varied. So therefore, an overall aim of the concrete repair code is to produce a document that provides a uniform set of requirements that is flexible and addresses overall repair issues. The LDP for the project is responsible for assessing the structures, from all the services from assessing the structures to specifying repair materials, developing details to produce quality assurance programs covering repairs, and advising the owner on future maintenance requirements to maintain a durable structure. One of the things that's been an obstacle, or some situations, building inspectors, building officials sometimes were insisting upon and holding engineers to standards for new construction for repair projects, which is inappropriate. And that led to some costly, unnecessary repairs or even demolition in lieu of rehabilitation. So we wanted to provide a document that you can show to a building code official and say, this is the standard we're using. One of the things that's really important is this concept of expected service life of the repairs. There's no requirement for expected service life or design service life, but as we all know, there's different options in repair, and the licensed design professional should communicate with the owner as to determine what the desired service life of the repairs are, and then design the repairs appropriately. So as such, working with ACI 562, you can use it to supplement the IBC or completely on its own. Okay, ACI 562 gets split into 10 chapters. The new version that's going to be published in 2025 will have a couple of additional chapters, really focusing today on the first couple of chapters, really chapter 1. Chapter 2 and 3, chapters 1 is addressing general requirements and gets into preliminary evaluation. Chapter 2 and 3, notations, definitions, references. I'm going to touch on some of these things really quickly. Structural assessment, chapters 5 and 6, repair design. And notice that we have a section on durability. We're actually talking about the durability design of repairs, which is a new concept for a lot of people. And then construction requirements. Some of the critical definitions are going to go through in the next slide. These are from the ACI 562 code, and they're also available on the ACI website. Assessment criteria, the codes of standards that you use in the evaluation. Rehabilitation is a process to get a structure back to a desired useful condition. Repair is reconstruction or renewal of concrete parts for the purpose of maintenance or to correct deterioration, damage, or faulty construction. One of the most important things we did in the repair code was to define what it means to damage. Damage is referring to a decrease in strength as a result of events. Deterioration is basically structures actually deteriorating or losing components or losing freeze-thaw damage are all causing deterioration. And then faulty construction is when a concrete structure, due to design or construction errors, does not have sufficient strength or durability. So those are all definitions that were provided to provide a consistent language framework for using ACI 562. Now, structural repairs are a little bit more specific. Those are restoring or damaged or deteriorated structure or increasing the capacity of structure. We're actually adding back strength that got lost. Retrofit in ACI 562 and an ACI is really intended as a modification of an existing member or system or structure to increase the strength or stiffness or ductility to address the seismic performance. We're really focusing on keeping retrofit associated with seismic, and then strengthening is obviously increasing the load resistance capacity. Structural evaluation, as you would expect, determining the current, confirming that current structure has sufficient capacity for current use. And assessment is the overall process for going through and making evaluating the structure and then determining the path forward. So going through chapter 1, the code section 1.2, which is the scope, The code applies to assessment, repair, and rehabilitation of existing structures as a code supplementing the IABC as a part of the locally adopted governing building code, governing existing buildings or structures, or as a standalone code. The intent is to safeguard the public, providing minimum structural requirements for existing structural concrete members and systems. And the user, and this is all building codes, the user is intended to be the LDP, the licensed design professional. Those are intended to be the critical person that actually understands how the code's actually working. Applicability, we already talked about building structures, so existing concrete structures, but also non-building structures when required by an owner or a building code official. And note that we actually took the building official was removed in ACI 56221. Section 1.3.1, applicable for assessment, evaluation, repair of existing structural components and non-building structures when appropriate. Applies to the foundation constructed of plain or reinforced concrete, including but not limited to typical types of footings: spread footings, mat footings, piers, pile caps, caissons, embedded. The design and installation of new pilings fully embedded in ground are regulated by the current building code. For repair of existing foundation members, the provisions of ACI 562 apply if not in conflict with the existing building code. For portions of the concrete piling in air or water or soil not capable of providing adequate lateral restraint through the piling to prevent buckling, the provisions of this code of ACI 562 would apply. So it applies to your foundations, applies to structural slabs supported on soils, not a slab on grade, but a structural slab supported on soil. The concrete portions of composite members. So when you have a concrete member and a steel frame, ACI 562 applies to the concrete portions. Pre-stressed and precast concrete, and both building and non-building structures, so marine structures, tanks, silos. What's it not applicable to? Non-structural concrete and aesthetic improvements. It's not intended for repair of non-structural concrete or aesthetic improvements, except, and this is a very important exception, if the failure of the repair creates an unsafe condition. One of the things we're trying to do is obviously prevent unsafe conditions. So if you're doing something like a overhead beam repair, and the failure of that repair would result in a piece of loose concrete, ACI 562 applies. Same thing on a facade repair. But if you're just applying a coating to change the look of a building, you don't need ACI 562 for that. Evaluation of seismic resistance and design. That shall be in accordance with the governing building code for seismic evaluation, if there is one. If not, you can use ASC 41. ACI 562 was not developed for seismic evaluation. And there's a very specific ASC 41 that's been developed for that. ASC 1C41 references ACI 369. Those two documents were really specifically developed for seismic evaluation, and we refer ACI 562 defers for them for that purpose. So let's step back. When should an owner start to seek professional help? And professional help for a structure, not for any other issues. So when a structure starts to, or a portion of it starts to exhibit signs of inconsistent behavior that's not expected or consistent with design, construction, expected design or construction, requirements at the time of construction, deficiencies, deterioration. So if you taking a look at the picture, you can see the sag in that girder from being overloaded for a long period of time. That sort of inconsistent behavior, maybe excessive cracking. Those are all things that point to the need for an owner to start to get an LDP involved. Evidences of structural deficiency or deterioration, where you start to see overhead damage, you start to feel unsafe in the structure. Those are all indications as to when an owner should start to get a licensed design professional involved. So what is the LDP responsibility? So at the start of a project, the LDP really has a lot of questions. The most important one when we're talking about the assessment is, are there any immediate unsafe conditions, and does the structure need repair? What codes apply? Is it a situation, or what code was it built to? Does it need to be satisfied current building code requirements? What loads should the LDP use, and what strength reduction factors are appropriate? If you think about different types of structures, a lot of parking structures many years ago were designed for 75 pounds per square foot. Current building code would allow 50 or 40 pounds per square foot. If you're in Colorado, maybe your snow loads compared to your original construction versus current have gone up significantly or changed significantly. So what load should that design professional be using, and what strength reduction factors? What evaluation and analysis methods? How good are we able to determine the damage? How well can we analyze it, and what's it all mean? And then, to what level should something be strengthened? Was the original design appropriate? Was the original design not appropriate? Or maybe there's a situation where something was designed for excess loads. Let's think about a warehouse that's being converted into residential. Maybe it's originally designed for 150 or 200 pounds per square foot of live load, and now it's going to be down for 40 or 50 because it's going to become a residence. What's the correct loads? What repair materials should be used to create a durable repair structure? Another critical question, what are the requirements for any temporary shoring that may be required? How do we maintain the load pass during construction or during the repair period? Or maybe immediate shoring is needed. And then how can the LDP ensure the overall success of the repair project? So the LDP is responsible for the repair process, from assessing a structure to specifying repair materials to developing the details to producing quality assurance programs covering repairs, and eventually advising the owner on future maintenance and repairs to maintain the structure once completed. And so what we'll do is take you through some slides on how we go through to do that. So evaluation by nature implies the use of personal and subjective judgment by those functioning in the capacity as experts. The evaluation should determine, to the best of the design professional's knowledge, the level of quality, adequacy, serviceability, durability of the existing structure, and based upon measured criteria or referenceable criteria, and the judgment of the design professional. Evaluation may require the design professional to gauge structural adequacy. Is some sort of temporary shoring necessary? So these are the sort of things that are necessary when applying and interpreting the ACI 562 code. Start to think about new systems design and construction methods. So any repair or rehabilitation or remedial construction system which does not conform to the code, but has been shown to be adequate by successful use, analysis, or testing, the design professional can try and use that, can bring that to the jurisdictional authority. So what are we talking about? For many years, things like FRP materials had not been fully integrated into the ACI codes. So many design professionals recognized that those were good materials that were available, and they needed special procedures to get those to be used. We're starting to see things like 3D printing that have not been generally recognized into the building codes yet. Can those be used in repair as a new technique? So ACI 562 does have provisions that are consistent with the ICC provisions on allowing a board of examiners or a jurisdictional authority to review those materials. That's also where the ICC ES reports come into play. So those materials can be potentially used and save your clients some money. So process for using ACI 562, it really starts with this, as I talked about, section 1.7, this preliminary evaluation. And then depending upon the results of that preliminary evaluation, we'll start with chapter 1, and then if necessary, go into a more detailed evaluation, which is addressed in chapter 6. So the preliminary evaluation, it's not intended to be a comprehensive study. Preliminary evaluations are by nature preliminary. they're general in nature. They may not be comprehensive enough to achieve the necessary objective, and you may need to do more work later. But they are intended as the first step to determine what's going on with the structure and a lot of how much we know about the structure. So it's carried out to develop an initial understanding of the concrete structure's behavior and existing performance. In other words, is it safe? Does the structure need further assessment? And is it in general compliance with the original building code? So a lot of these questions that come up with respect to preliminary assessment has to deal with the extent of documents that are available. What do we know about this? You're looking at the picture on the right, you're starting to see some spalled concrete. That's creating, in my mind, that's creating concern about safety. The extent of documents, do we have any information? Do we have any documents at all? So really preliminary evaluation, we're consisting of getting familiar with the original building code the structure was built under, any review of any existing plans, specifications, testing reports, any existing documents related to the project. Talking about visiting the structure with the plans to verify the existing structural plans match. A lot of times they don't. Marking, determining what may have changed, what type of previous repairs, maybe some simple calculations to assess material properties. And the other one that's always critical to me is what's the type of damage that you're dealing with? Am I dealing with a precast parking garage in which I have some damaged, or I'm going to call them worn out sealant joints between double T members and possibly some camber clips? Or am I dealing with a multi-story post-tension building that has significant damage to the post-tensioning system? It's all types of different structures out there. And what I can say about certain things from a visual inspection, I certainly cannot say about other things. So the objective of reviewing the existing documents is to collect information. It's not, at this point, we're not doing a comprehensive study. We're trying to evaluate the existing information about the structure within the work area. Again, we're going to confine it to a work area and make an initial determination of its adequacy to withstand in-place environmental conditions and design loads. We're collecting information on anything we can determine about the design, the materials, how it was built, service history, and then making a note of what information's missing or not available. When there's no information available about the structure, the survey should compensate by determining recording dimensions, structural components, presence of reinforcing steel, whether we're using some GPR, tachometers, direct inspection. We're looking at all that stuff to figure out what's going on. Some design information, original codes that may have been used, available, what construction documents, shop drawings, placement drawings for reinforcement, other things you can get into, textbooks at the time of construction, copies of the old building codes. All of this information can be used as part of your preliminary evaluation or part of your comprehensive evaluation. When it's available, we can look at certain types of materials information, concrete test reports from initial construction, submittals, concrete mixture proportions may be available from batch tickets, mill reports from the cement or the reinforcing steel, protection systems. That's some of the material that may be available. And then obviously getting more into it, various original construction documents may have been retained, and they're very helpful in learning about the construction methods, materials, problems encountered. So things we may be looking for, correspondence between members of the design team, results of tests on the concrete from initial construction, quality control data, diaries kept by construction team. That's a little unusual to find. It's always helpful to have job progress pictures, as-built drawings, survey notes, records. All types of information may be available if you ask the right questions and are willing to search for it. Information regarding the foundation, soil bearing capacities, geotechnical reports, things like allowable bearing capacities, location of the water table during construction. All of this information can be used to help us make a decision about the structure. And then finally, critical Documents that relate to the structure's service history should be reviewed to learn as much as possible about the maintenance and previous repairs, any previous work. So if possible, records from former owners, current owners, reports from prior consultants, reports maintained by the owners of adjacent structure. Talk to the operations manager of the building manager, maintenance personnel. Depending upon the area that you're in, you may want to review the seismic activity or geological activity. Insurance reports, records of damage to the structure if there was a fire or wind or snow. All this information may be available for review. And then obviously you're going to flavor all of this information with your own personal experience with similar structures in the geographic area. Is it, want to understand the age of the structure, its environment, how it was placed, and then what type of materials we're using at the time of construction. And finally, one of the other critical things for historic structures, some of the information sources that you can get, the Library of Congress, National Register of Historic Places, State Preservation Societies, all these other sources are available and may have useful information about the service history of the structure. Then, as we keep going through as part of our visual preliminary assessment process, we'll get into a visual inspection. We're going to visit the structure, actually determine if our plans and the actual structure match. So we're checking in place geometry, looking for signs of material deterioration, distress, some of the things we may see, some of the things we may actually see. Excessive deflections, what does that mean? Typically, there's certain amounts of deflections that you can see and are visible to the eye. And then a lot of times something will pop out to your eye that just doesn't look right. And that's really what we're terming an excessive deflection. Evidence of water infiltration is a big problem. Atypical cracking problems. As most of us know, all concrete structures crack. Just is the cracking that you're seeing consistent with what you expect to see for similar structures, or is it atypical? And then things like vibrations. A lot of times if you're sitting and working in a parking structure and a car drives through, is the structure moving? Can you feel it move? Does it feel like it's moving too much? All that information and stuff that we're thinking about as part of our assessment of the structure. So our preliminary findings, the preliminary judgment is based upon personal experience. And what we're trying to determine is some information about the condition of the structure, is there faulty construction and extent of deterioration. And we're trying to find out really if unsafe structural conditions are present, perhaps as far as, as bad as substantial structural damage has occurred, if there's any faulty construction. And really a lot of what we're doing is determining the need for future measures at the structure, whether they're immediate and what type of repairs. If we are finding faulty construction or we're finding unsafe conditions, there's maybe need to report some of these conditions. That's discussed in ACI 562. Then our preliminary analysis. So depending upon what we're seeing, if what we're seeing indicates severe distress, we should contact our owner immediately to identify where some shoring may be needed. Maybe we need to stabilize some areas. Maybe we need to limit access to certain areas to get rid of the unsafe conditions. Now, substantial structural damage refers to damage in a structure that's resulted in a significant, typically more than 1/3 of the decrease in the gravity or lateral load resistance of the structure. And typically, we're not going to be able to determine that from a preliminary evaluation, but it's really the first step necessary that we're going to be going down that path. So a lot of that information that we gathered, we're going to be using that to start making some decisions about the structure. And how are we going to do that initial preliminary analysis? Maybe doing some simple calculations based upon either records from available materials testing or historic data, which is presented in Chapter 6. Now, the preliminary analysis. When material test results are unavailable, what we can do is use historic properties based upon typical values from the time of construction. Those are typically conservative, and those are shown in Chapter 6 of ACI 562. And then our focus really should be on determining the critical gravity load resisting members, such as columns, the walls, and then follow that by assessment of the lateral resisting. If we have material properties available, we can use that. If not, we can use historic. And then always in these calculations, we're trying to consider the in-place geometry and any observed deterioration in our calculations. So for the purpose of our preliminary evaluation, what are we going to use for a code? We can use the original code, the current building code, or one of the assessment criteria presented in Chapter 4 of ACI 562. And as you get into the presentation tomorrow, you get a lot more details on the assessment criteria in Chapter 4. So what happens? What to do when the preliminary evaluation and preliminary analysis reveals unsafe structural conditions? Okay, if we do find unsafe structural conditions, they can vary in severity and vary in significance. The code of ACI 562 section 1.5.2 is going to tell you as a design professional, report that unsafe structural conditions in the work area to the appropriate authorities with the recommendation that they immediately alert the contractor or owner, do something to make these unsafe conditions safe. What can that mean? Well, let's say we see loose concrete on the facade of a building or on the soffit. That loose concrete can be removed. We could close the area where that loose concrete is present, so there's no pedestrian exposure, no vehicle exposure. Or we may find something worse. We may find that the structure needs, in our opinion, as a design professional, structure needs some type of shoring. So we need to make that recommendation to the owner. And in some situations, we would be reporting that to other appropriate authorities, depending upon the requirement of the municipality that you're in. So we're addressing those unsafe conditions as soon as possible. But the more common one is our preliminary analysis will indicate that a structure is adequate if maintained properly. There's a couple different iterations here. Adequate, but it's going to need some work in the future, so there's going to be some prevent continued deterioration. Inadequate, we may be okay if we keep the loads reduced, or inadequate and needs immediate repair. Inadequate and beyond repair. And then there's some situations where we just don't have enough information in our preliminary evaluation to create a definitive conclusion, and more investigation is required. And that would be addressed in Chapter 6. So when required by our contract, we'll provide the owner with a report documenting the materials that are shown, the original building codes, the project documents that were reviewed, any prior repairs, locations of damage, any recordings of actual member cross sections and deviation from expected tolerances that we see. And this is when required by the contract that the design professional has with the owner. A couple important things. Typically, a visual inspection alone is not sufficient to assess corrosion and whether or not reinforcing steel is corrosion. Yes, you can see spalling. You can see corrosion damage on bars, but you really can't tell anything about the steel that's still, visually can't tell anything about the steel that's not present on the surface or where no damage has occurred yet. Similarly, you can't tell much about things like post-tension structures where the post-tensioning tendon is protected by a sheathing. However, the visual inspection is a good method for initial assessment when the design professional has experience and uses sound judgment. So let's move into talk some more about concrete distress. And really for the next closing portion of the slide of the presentation today, we're going to be talking about the distress of concrete structures and some of the things that cause concrete distress, why concrete's cracking. And these are the things that we'll be looking at when we're actually evaluating existing structures and trying to understand the next step. So some of the deterioration that may be documented are crack pattern, and I'll talk about that in the next couple of slides. So when we're talking about cracking, the design professional really has to understand what these cracks mean and determine why they occurred, and then provide the owner with a sound opinion as to the cause of the damage based upon their knowledge, experience, and judgment. And then other things may require non-destructive testing, removal of concrete to get a better idea and confirm. So in the next couple of slides, we're going to provide an overview on some of the types of cracks that an engineer may see in the field and try and give some idea of what they mean. These are just a few of the many types of cracks that you will see in a reinforced concrete structure. But we want to give you an overview of these to talk about it so you can kind of identify drying shrinkage cracks, freeze-thaw damage, volume change effects, alkali silica reaction, which is one of my favorites, and finally sulfate attack. So drying shrinkage, as we all know, when we mix up reinforced concrete, we always end up providing a little bit more water in the concrete than is actually needed for hydration of the cement. And that excess water is available, and that can evaporate, resulting in a loss of moisture from the cement paste or drying. And when that happens, the constituent materials can shrink by about as much as 1%. Now, fortunately, the aggregate particles provide restraint to that shrinkage and reduces the magnitude of the volume change to maybe something like 0.06 or 0.05%. On the other hand, when we expose concrete to water, it's going to increase in volume. And typically the volume increase can be the same ordering of magnitude as that observed due to shrinkage. Another thing that happens is restraint will be provided typically by another portion of the structure, subgrade. Now, once that happens, we start to lose the moisture, we start to develop tensile stresses. Once our tensile strain exceeds the strain capacity of the concrete, we get a crack and people get unhappy. That's the typical problem. So what does that look like? You have the original length. If you had unrestrained shrinkage, if there's no restraint, it would just shrink and get shorter. More likely, we have some type of restraint, so we end up developing a crack. We have differential shrinkage. Okay. Freeze-thaw damage. Deterioration of concrete occurs once the concrete becomes critically saturated, which is approximately 91% of its pores are filled with water. When water freezes to ice, it occupies 9% more volume than that of water. That's why ice floats. If there's no space for that volume expansion in a porous material, the water inside the concrete will freeze, causing distress in the concrete. And you can get this freeze-thaw damage. You get this typical scaling pattern where the paste is actually popping off and the aggregate remains intact. So what does that look like? What's the mechanism? In non-air entrained concrete, as the water, which is a weak alkali solution, cools, ice crystals form in the large capillaries. Osmotic potential develops and causes the movement of water from unfrozen pores to the frozen ones. More ice forms until the cavity is full, and once it's all full, cracking starts to occur. So basically what's happening is this water wants to freeze, it's expanding, it's got no place to go. Eventually it pops the concrete. That's on non-air entrained concrete. If we have air entrained concrete, we specify adequate amount of air depending upon exposure conditions and the size of the aggregate. And the air voids provide space for the expanding water to move into, and that minimizes or prevents concrete cracking. This is the simplest explanation we can do for this one. So if we have adequate curing and drying before the first freezing cycle, we have air voids inside the concrete. Water can move into those air voids and finds an escape path there that provides basically a relief valve or spots for the water to freeze into. So then when it's exposed to freezing conditions, it doesn't crack. So what do we want to do? We want to use the lowest practical water cement ratio and design an appropriate amount of air based upon the exposure. And if you look in ACI 318, you can find a discussion of exposure categories F0, 1, 2, and 3 that will talk to you about how much air is necessary in the concrete to prevent damage. So what does it look like? That's the more important question. What does it look like? So the typical failure pattern in a non-air entrained concrete is, remember we were talking about the water is expanding and the water's inside the paste. As that expands, we typically will get this cracking parallel to the surface, as you can see in the slide. And that occurs after the paste has become saturated with frozen water. Okay, so a couple photomicrographs. This is failure without air-entrained concrete. There's critical saturation of the paste. And then on the other side, we have air-entrained concrete, and the photomicrograph shows the concrete experiencing freeze thaw. So we get critical saturation of the aggregate. Once the paste had adequate air entraining, but the aggregate itself was porous, and the water got into the aggregate and actually started to expand and cause the damage. Some of the aggregates that may be prone to freeze thaw damage when critically saturated are cherts, clay-bearing limestones, and some of our lightweight aggregates. So freeze thaw damage. The other problem we have is volume change as a result of shrinkage or expansion. This can be thermal deformation, which is a result of either the heated hydration in mass concrete or changes in air ambient temperature, which is in all concrete. This is a little bit of damage from very high heats of hydration. This is in Texas. Okay, so thermal cracks are caused by excessive temperature differentials in the mass concrete. There appears random pattern cracking on the surface of the member. Checkerboard or patchwork cracking due to thermal effects will usually appear a couple days after stripping the formwork. Temperature cracks in pavements and slabs will look very similar to drying shrinkage and typically occur perpendicular to the longest axis of the concrete. They become apparent at any time after the concrete is placed, but usually within the first year or summer winter cycle. So because of these thermal cracking, the hydration of the cementitious materials generates heat for several days after the placement, and that heat dissipates quickly on the surface in thin sections and doesn't cause a problem, but in thicker sections, the internal temperature rises and drops slowly. When the surface cools rapidly to ambient temperatures, there's a huge difference in temperature, and the subsurface contraction due to cooling is restrained by the hotter interior concrete that doesn't contract as rapidly. And that restraint causes tensile stresses that can crack the surface concrete as a result of this uncontrolled temperature difference across the section. In most cases, thermal cracking occurs when concrete surfaces are exposed to extreme temperature rapidly. The concrete members will expand and contract when exposed to hot and cold ambient temperatures, respectively. Cracking occurs if this bulk volume change from temperature variations is restrained. This is sometimes called temperature cracking, and is a later age, longer-term issue. So the hydration, so basically what's happening is we have a concrete member in a big delta T, and we have thermal stress as a result of that difference in temperature, where the core is staying hot and the exterior is cooling, and that difference in the thermal stress leads to tensile cracking when the tensile strength is achieved. So the hydration reaction that's occurring, which is generating the heat, occurs when the cement and the water are mixed together, and the amount of heat generated is a function of type of cement and its fineness. And the peak temperature is a function of initial temperature, how much cement is present, and the geometry of the member. But basically, the more important one, the larger the member, the greater the potential for thermal cracking. And then the type of formwork. Is that formwork providing insulation itself? So what do we want to do to prevent this in new construction? We're going to limit the temperature rise. We'll use a cement with a lower concrete with a lower cement content. In hot weather, we want to basically start with a colder concrete, chill the water, chill the aggregate, or use ice. And when possible, shade the area being constructed to avoid solar heat gain. reduce with thermal moments, we can vertical formwork, we can keep the formwork in place to more slowly cool the top surface, cool the exterior surfaces of the structure. And sometimes we can use different aggregates that have a lower coefficient of thermal expansion, like a limestone, to have a little bit less expansion under these temperature changes. So thermal deformation damage from change in ambient temperature can be seen in these pictures. Some of the pavement sections shown in this one, you can see the concrete has a sidewalk set above the pavement. There's no isolation or expansion joint. Over time, concrete, whatchamacallit, expanded and pushed the concrete out, causing the cracking. So the lack of joints in this situation contributed to the damage. So alkali silica reaction, sulfate attack, these are basically two different types of chemical attack. In alkali aggregate reactions, alkalis in the cement are reacting with either siliceous or carbonates in the aggregate. And when the presence of water, those materials will form gel products that are expansive that cause cracking. In the case of sulfate attack, we can either have an internal or an external source of sulfates that can SO4 materials. They can either be in the soil or in the water or internally in the concrete, and those will react with some of your Portland cement hydration products and cause expansive formation that also causes cracking. The expansive reactions from the ASR typically have a map cracking or an alligator pattern, and that's a result of the expansive reactions at the aggregates causing that popping to occur. So the pictures, there's two slabs. This has been, one's cracked, one's not, and that's Tuscaloosa Lock and Dam. And it's concrete with different cements. One was a high alkali content, the other was a low alkali content. And that difference in the alkali was the material that was driving the reaction, allowed the aggregate to react in the one and not to react in the other. So what does that look like? It's typically the ASR gel is typically a white deposit. It's efflorescence-like. And in unrestrained concrete, the cracks will develop into a random pattern. Map cracking is commonly called. Restraint cracks tend to run parallel to the direction of restraint or parallel to the direction of the reinforcement or vertically in a column. And the cracks may exude that white gel, which we just mentioned. It's white deposits. Pop-outs may occur where individual pieces of aggregate have expanded and disintegrated beneath the surface. Typically, ASR reactions take time. So it's typically, in most structures, it's a couple of years after casting, but it could be earlier with some aggregates. And in some aggregates, it may not appear for 40 years. So let's talk a little bit about the mechanism. As I mentioned, the alkalis, which are coming from the Portland cement, or some cases they can be external, are reacting with the silica and water to form a calcium alkali silicate gel. The gel takes up space and so takes up the pore solution and expands, which eventually will cause cracking. And ASR is only going to cause damage to concrete when three factors are present. You have to have enough alkali, a critical amount of aggregate, and sufficient moisture. If you have any one of those three things, the ASR is not going to occur. But let's look a little bit closer at some of the damage from some of the pictures. Look at some petrographic images. The reaction products appear as the white rings around the reactive aggregates. And the reaction products will appear green when an uranyl acetate solution is applied to a fresh fractured surface under a UV light. So let's talk a little bit more about sulfate attack. All right, so sulfates in the soil or water combine with tricalcium aluminate in the cement. They produce etchingite, which causes expansion and deterioration. To prevent sulfate attack, you can use a type 2 cement, or these days it'd be a type 1L cement. You could add in a class F fly ash. You can use a slag, or you can drop the water cement ratio, make the concrete a little bit less permeable and less water infiltration. So what does this look like in some of the pictures? Those are 6 by 6 by 30-inch beams that were used in a sulfate exposure test plot in Sacramento, California. The specimens were designed with different water cement ratios, different types of cement, and exposed to for 6 to 7 years to sulfate saturated medium. So basically they were wetted and dried, and with the wetter and drier being a high sulfate solution. So the deterioration of the concrete results in basically complete disintegration of the concrete. All your paste breaks apart and you got nothing left but a pile of aggregates. It turns to mush. The rate of reaction is a function of how much sulfate is present, how much water is present, and then ambient temperature and humidity, ambient temperature and humidity, and then the concentration and the type of sulfate that's present. The sulfate attack can be minimized by decreasing the water cement ratio so that the concrete's a little bit less porous, minimizing cracking so we're not giving a path for the nasty water to get in, and then selecting appropriate cement and other cementitious materials. So it gives you a couple more, some more specimens of same cement type in this situation with different water cement ratios. You can see how the specimens with the higher water cement ratio on the left are much more deteriorated than the ones on the right with the lower water cement ratio. Okay. Corrosion. Probably I spent more time investigating corrosion damage than anything else. It's the #1 cause of concrete failure. As high as $468 billion. And that does not include the loss of revenue. That's just the cost for doing repairs. So what we're looking at on the left side is a pileouster that supports a seawall that is cracked due to corroded reinforcing steel. And on the right side is a marine pile supporting a dock. The rebar behind this corner expanded and caused the corner to crack. So what's going on? What's causing this damage? Reinforcing steel and concrete is protected by a high pH layer that forms on the reinforcing steel. And as long as that protection is present and the concrete's nice and dry, that reinforcing steel is not going to corrode. What happens over time is chlorides will penetrate into the concrete and they'll break down that high pH layer that's present on the concrete. And then once that happens, once sufficient water and oxygen are present, we'll start to get cracking, we'll start to get corrosion, and eventually, once the reinforcing steel expands sufficiently due to corrosion processes, we'll get cracking. Start to see here, start to get more expansion, and then eventually we're going to form delaminations and spalls in the concrete. So some of the factors that are affecting the corrosion are the quality of the concrete. How impermeable is the concrete? How much cover is present? Is it 3/4 of an inch? Is it 1.5 inches? Is the moisture condition? Is the concrete saturated? Is it draining properly? Is it in a tidal zone? Or is it someplace where it's going to stay clear and dry? Temperature. Obviously, being a chemical reaction, the higher the ambient temperature, the higher the rate of corrosion. A combination of chlorides and sulfates can get together and cause even more damage, where you have the chlorides attacking the reinforcing steel and the sulfates are attacking the cement. Oxygen needs to be present. For most cases, there are situations where corrosion can occur in low oxygen environments. And that's a little bit more complicated, and we're not going to talk about that today. The so-called microbial-induced corrosion can occur. And there's also the process of carbonation, where, and we'll talk about this in one of the slides, CO2 from the atmosphere reacts with the Portland cement to decrease the pH. And that also leaves the concrete, the reinforcing steel susceptible to corrosion. So concrete has a naturally high pH. And we're not going to get deep into the chemistry here, but that means the concrete is alkaline, the opposite of acidic. Steel naturally has a reaction with the alkali environment of the concrete that forms a protective layer on the reinforcing steel. So we start out with our new concrete with a high pH, and this is called passivation. That's our nice green layer, and that's not epoxy coating. That's a passivating layer that's present on our reinforcing steel. And this passivating layer is one of the things that makes concrete and steel a durable combination. Unfortunately, there are contaminants that can lower the pH of the concrete. When this happens, the concrete no longer maintains that passivation layer, and corrosion can start. And the two, as we mentioned, the two most common ones are carbon dioxide and chlorides. So what is the passive? So what's going on here? Yep. There's two main disruptors to the passivation. There's chlorides and carbon dioxide. So let's look at exposure to carbon dioxide and moisture. This is the process in which carbon dioxide lowers the pH of the concrete. It's called carbonation. And the carbonation occurs when the CO2 reacts with free calcium hydroxide in the concrete to form calcium carbonate. And that CO2 enters into the concrete and reacts with the water, forming carbonic acid. And that acid, along with the reaction of the CO2 with the calcium hydroxide, acts to decrease the pH of the concrete. Now that level of the depth of penetration increases over time. So once you see initially the concrete protected, now over time it's going to reach down into the level of the reinforcing steel. Now, once we get down, once that passivation layer is disrupted, the corrosion can start. In a normal environment, it's a very slow process, and it typically will take 25 years for carbonation to reach reinforcing steel that's 1 inch of cover. However, situations where there's a high CO2 environment, highway tunnels, industrial facilities, that concrete may carbonate faster. Now, the other thing that happens is obviously chlorides, water, and oxygen penetrate into the concrete as well, and also the chlorides will act to form, destroy our passivating film as well. So the time to corrosion is a function of the steel cover depth and the concrete quality. So the second way that pH gets, that passivating layer gets damaged is by chlorides and moisture. Chlorides come from a lot of different sources. They can be salt water, de-icing salts, industrial processes, or we can have chlorides from the original concrete mix, either as an intentional admixture, which is not permitted anymore for structural concrete, but it's been common in the past, or impurities in the water or the aggregates used in concrete mix. So the chlorides ride into the concrete on the water, and they manage to saturate in down to the reinforcing steel. As they get there, they eat away at the passivating layer. And then once that passivating layer is disrupted, that leads to corrosion, allows corrosion to occur. So what can that look like? This is a picture from VDOT where there's very concentrated cracking at a leaking deck joint. And actually, that concentrated corrosion led to the reinforcing steel shearing or rupturing at the deck, at the joint level. So concrete cracking due to corrosion, bars, if we have bars close to the surface, widely spaced, the cracking, the bars will tend to fall away, or the bar will tend to have vertical cracking. If the bars are away from the surface, then wide space will tend to get localized spalling. And the bars away from the surface and more closely spaced will get a delamination. So when we're thinking about our assessment, those are different types of cracking patterns that we have to be aware of and understand the implications of what they mean. So how do we keep our concrete safe from chlorides and carbonation? Obviously, we want to limit the chlorides in our concrete, so make sure We're not using things like calcium chloride as an accelerator or making sure our aggregates are not accidentally contaminated. Reducing the water cementitious materials ratio, trying to create a less permeable concrete, so we're not allowing water in as freely. Adding in a fly ash, a supplementary cementitious material to reduce the permeability of the concrete. Same thing with a slag, a ground granulated blast furnace slag. Silica fumes, another way to decrease the porosity of the concrete. Corrosion inhibitors. And so the other one, so we talked about some of these damage mechanisms. Now let's talk about some design defects. Things can be under-designed, so there's inadequate strength, improperly detailed, or you can have something like a lack of expansion or isolation joints, so the structure can't deform. Bottom left is a punching shear issue, I believe, at a column. And then up at the right, there's a reverse shear crack in a concrete girder. So this is something where we had inadequate detailing. These are two girders. They're supported on a pier without providing any sort of neoprene pads or allowance for movements. And this structure was still going to move. This resulted in the cracking of the pier at the column. The cracks were not actually a movement joint. They actually basically created its own joint. Structure created its own joint. The upper right picture here, this is a structural crack. It's a severe fault in the concrete structure, almost inevitably going to cause a significant problem. The cracks is primarily due to inaccurate designs and construction faults. Could be inaccurate overloading. In the lower left corner, there's spalling as a result of corrosion. And so these steel reinforced members, they were close to the surface. And as you can see, there's a joint which also helped to collect water. And as that water penetrated into the concrete, the low cover steel was corroded. And that led to spalling of the area in the unsafe condition. Some types of construction defects that may cause damage to a structure. Additional water to the concrete, which will decrease the strength and will also increase the potential for shrinkage. A lack of curing or early termination of curing. Again, this can lead to cracking. Poor execution, formwork, surface preparation, consolidation issues. So let's talk about this. This is a picture from Michael Sprenkel. And this is intended to be a reinforced concrete column, I believe. And it looks more like looks more like something where they try to see if we can get any concrete through all the reinforcing steel. So what's supposed to happen? Concrete, as we know, when it's placed, is consolidated using what we call concrete vibrators or vibration. And the vibrators would basically liquefy up the mortar fraction of the concrete to allow it to flow, drops the internal friction between the aggregate particles. And it's a two-stage process. So the concrete, when you vibrate it, will slump down and flow. And then there's the deaeration. As a result of that, during that process, you're going to deaeration of the mortar. When you stop vibrating it, the friction between those aggregate particles comes back. So what did that picture look like when they try to place some concrete in it? Vibration only works if there's actual space for the concrete to go. And if you have a wall of reinforcing steel with no space for the concrete to pass through, it's not going to work, and you'll end up with something like this, which is obviously something that's not going to work and need to be replaced. Let's see some more close-ups. And some typical, actually I don't want to say typical, but some situations where there's been inadequate vibration, inadequate consolidation of the concrete itself. And here, where they tried to get the material, the concrete, to flow underneath a void in the formwork, and it didn't quite make it all around. Different types of overloading can occur and damage a structure. The overload in the upper right picture was an excessive gravity load that basically failed the beam and needed to be shored immediately because it was about to collapse. And then the lower right corner was a more atypical one. This was a result of flooding during Hurricane Katrina, where the flood waters move through and pop that panel off the concrete structure. If you're interested and want some more information about the cause and control of concrete cracking, there's some references on here and that are available from ACI. And that's really the last slide in the presentation today. So I see we do have some time left for questions. And I want to encourage everybody to continue on with parts 2, 3, and 4 of the seminar series, which starts tomorrow. And those parts 2, 3, and 4 will take you through use of the ACI 562 code for further evaluation of reinforced concrete structures, understanding Chapter 4, which provides different demand to capacity ratios as delimiters for what types of repair and strengthening may be necessary. Talks about the load and resistance factors that are being used in concrete repair projects. And then next week, Monday and Tuesday, Dave Tepke and Kyle Stanish will take you through repair and durability design using ACI 562, and Kyle will finish up with some really good examples. So I guess with that, we'll see if we have any questions available. Katie.
Keith, thank you so much for going through that history of repair and discussing some of our cracking mechanisms that are applicable. We do have a couple questions. So the first question we have is it allowed to use other repair codes for buildings in the USA based on the owner's requirements?
It's an interesting question. I've not gotten that question before. Other repair codes based upon owner requirements. So I guess my answer is going to be, yeah, my answer would be yes, provided, and without knowing more of the specifics, you would have to have if there's a jurisdictional authority, they would need to be okay with the other repair code and that being used. Obviously the owner, as the question indicated, was okay with that other repair code being used. And as long as the jurisdictional authority approved it, I would not see an issue, provided you had that jurisdictional authority approving it and the owner being aware of it.
Okay. Our next question is, why is a performance repair code preferable to a prescriptive one?
Good question. So the performance-based repair code is really providing, in the simplest way to explain it, the repair design shall consider something, the need for durability. And what it inherently recognizes as a performance code is that there's multiple ways to achieve, I'm going to just say durability. And depending upon depending upon owner requirements, depending upon budgets, you may have there's different options. And by having the performance basis, we're allowing the design professional to satisfy the owner requirements without being prescriptive and really sort of optimizing the repair to what the owner needs. And it's intended to give both the design professional and the owners more flexibility. Let's expand that a little bit. Let's say, this was never going to happen with ACI 562, but let's just say ACI 562 as a prescriptive requirement said every repair shall be designed to have a minimum design service life of 25 years. Well, that forces owners to spend more money than they want to on a concrete structure, and that's an owner's prerogative. They have to maintain the structures in a safe manner. They don't need to. They can have make that decision to spend money down the road or do other things. Or let's say ACI 562 said all damaged concrete structures shall satisfy current code requirements. Well, that's atypical with historical practice. It's not really needed. There's plenty of concrete structures that are designed for prior codes that are safe. There's no reason to strengthen them. So we're providing the performance requirement for the engineer, the design professional, and the owner to determine the extent of repair may be required, consistent with the provisions of Chapter 4. So really, the performance requirements were intended to give the design professionals more flexibility.
Great. Our next question is, what information is available to engineers when assessing historical structures? So where would they go to get materials properties on square bars or smooth bars or other?
Okay. So one of the good things, one of the great resources and I'm not plugging any specific reference, but I'm going to tell you about one reference that I've used a lot. There's a CRSI book. I don't remember the year it was published, but if I could turn around, I could almost reach it. It's behind me, but it's a CRSI book that has a lot of that information. I think it's historical concrete structures. There's a lot of information on there. And then we've actually, in the new version of ACI 562, which is being developed, there'll be more information about that, because development of some of those historic bars was very different. So we're providing some more information about that. But the CRSI reference handbook is probably the best one that I can think of. Beyond that, you get into, if you do some searches on Google, you'll find some really interesting stuff about historic structures. I was working on a con reinforced structure a couple of years back, and there's actually some information available on Google from people who are publishing old con manuals. And then I think a couple of the references that I mentioned, if they are actually historic structures where there's documentation on the historic nature of the structure, that's a great source of information. If they're registered historic structures, you could probably find that information. Hope that answered the question.
Thank you. Yes. Our next question, does the code address specific deterioration issues? For example, using aggregate that might cause deterioration, such as a pyrrhotite? Sorry.
Pyrrhotite.
Thank you. And how can you identify pyrrhotite failures, and how would you fix such a structure?
Great question. The code's not specific about identifying specific types of damage or specific damage mechanisms. That would be something that's very complicated. And I think as the code progresses, it probably will get into that a little bit more. How would I identify and how would I address pyrrhotite damage? It's a good question. The people that aren't familiar with it, pyrrhotite is a sulfate mineral that's now causing we're going to call it slow expansion damage to reinforced concrete structures in certain geographic areas. It's very concentrated in a couple of different areas in the US and Canada. And I think the only way to identify it is via either specialized chemical tests or through petrographic analyses. And even then, I think it's difficult to expand it. How would I repair it? I think it really is going to depend upon the extent of damage that's present. Is it something that's caused a little bit of surface cracking or some small amounts of cracking? I think if the structure was able to be kept dry, I think you have a chance of slowing the reaction down, because it's like a sulfate reaction. It does require water. But I have not been involved with any pyrrhotite damage or repairs. I know there's a lot of people that are basically removing and replacing or doing other types of repairs, but I haven't been specifically involved, so I don't want to comment on specific mechanisms to repair it, the pyrrhotite.
Okay. Stepping back to the mechanisms, there's a question about slide 108, which you were talking about alkali-silica reaction. And the question is, if you would repeat what you stated about the photo on the left. The attendee says, I would have noted that as efflorescence, but it sounds like it might not be efflorescence. So the question is, how do we differentiate ASR, the gel, and the efflorescence?
All right, so again, a good question. You're right. You do look at it, and it does look like efflorescence. My joking self says, oh, you got to taste it, but that's not the answer we're looking for. You would actually have to take a sample of it. All right, so what we're going to do, we're going to look at the overall cracking pattern. we're going to try and possibly identify a sample of that, material, and bring it back to the lab and test it to see what it actually is. Be one, and then I would be looking at the cracking pattern for the picture on the left. There's a couple things. Obviously, there's a huge amount of water that must be moving through that structure. So that's one thing I'd be really, really concerned about. But I really want to see what the cracking pattern is, because if you would, and with that much ASR and that much water movement, I'm guessing that you could get a fairly good idea that it's not just leakage coming through there causing that efflorescence. So I think you'd tend to think that there's another problem going on, which may, continue to drive it. The picture is from New Brunswick. I'm not that familiar with New Brunswick aggregates, but I know there are some really bad aggregates in Quebec that are pretty ASR susceptible. So that's where, again, local knowledge comes into play. And then just to contest and confirm what is actually present in that exuded material that would be the sort of the gospel truth to that.
Okay, we do have another slide-specific question.
Great.
So the question is for slide 128, which shows some structural cracking and some spalling. The attendee states, did you mention the believed cause of the structural crack? They may have missed it when you said it.
Well, lower left is low cover concrete and spalling. And most likely we're actually getting, there's a horizontal joint there, so we're attracting and water's somehow stopping at that joint. The other one appears that could be there's a couple things that look to be, that could be a development failure where the bars have slipped is my one opinion, but I don't, actually, since Khalid and Alawi put the slide together, I don't have any more information about that. But my one guess is the way that crack formed. It's a development failure, and the bars have actually slipped. So that would be another one, something else to think about. It doesn't appear to be crack corrosion related, just because I don't see any signs of corrosion products. So I would say that's most likely a slippage.
Okay, now a non-specific slide question. Okay. Is preliminary assessment required or recommended on all repair projects?
So, and it's a good, I mean, to me, I always think that there's going to be a preliminary evaluation as part of the process. If you chose to, you could go straight into a more detailed evaluation process. It's really like, I think it's a lot of it is how you approach, a project. And so much of this is dependent upon what type of structure you're dealing with, if you have some indication of what the damage is present, and what sort of information that you have about the structure. Let's just say I have a 50-year-old warehouse and I know absolutely nothing about the structure. I don't know anything about the concrete. I don't know anything about the strength of the reinforcing steel. I just see a whole bunch of corroded reinforcing steel on the soffits of the structure, and I have no idea what the prior loading was. My preliminary evaluation is really going to take me about 10 seconds, that I need to go into a more detailed sampling and testing program to get an idea what's going on. And let me take a different structure. I have a 10-year-old precast parking structure, and I have structural design drawings, I have shop drawings, and I have individual piece drawings for the let's just say it's double T members. I have all that information, and I go out and I see, I think I mentioned this earlier, broken camber clips and failed sealant joints. I'm also comfortable with the person that did the precast design. I think they were competent. So then that's a very different that's a very different type of project, where in that situation, my preliminary assessment, maybe my preliminary assessment is going to be focusing really on those camber clips, and there's no other signs of deterioration in the structure. So it's really I think it's really very project specific. And, there's kind of a fine line between what's preliminary evaluation and what's detailed evaluation in some things.
Okay, our next question is actually sort of looking for some advice. So how can licensed design professionals gather enough experience to be able to make professional judgments that are required by using this code?
It's a good question. And I think that really goes back to everybody as an engineer should always be learning. I've been practicing, I've been doing engineering 25 plus years of practice, and there's still days, every day I see something new and different. I think you got to be out in the field looking at it, but you also got to be thinking about continuing education. You got to be going to, whether it's, ACI or ICRI dinner meetings where people are talking about, existing structures, talking to people at these, talking to people in meetings. It's really having, I think it's really establishing that mindset of continuous learning that we need to have. We have this question a lot. ACI is producing a couple new code documents in the next couple of years. ACI has published ACI 440.11. That's a document on how to design reinforced concrete structures using FRP bars in lieu of traditional reinforcing steel. That's a new document that, a lot of design professionals were never exposed to. There's going to be a code for FRP repair. There's going to be a durability code coming out in a couple of years. So there's a lot of new documents that none of us learned about in school. So we need to have the mindset where we're continually learning and, accumulating our PDH credits and everything else. And then, obviously trying to work with some people. If you're a young engineer, trying to work with some people that have experience so that you can learn some stuff from them.
Okay, great. So you mentioned a new code on FRP 440.11. Following up on that, do you recommend using FRP bars to mitigate corrosion in concrete?
Yes. FRP bars can be extremely useful as in repair projects. Let's step back. There's multiple types of FRP. There's FRP wraps, there's FRP bars, there's near surface mounted bars, but they have a huge advantage in terms of being corrosion resistant. And you can see a lot of repairs that have been done using FRP bars as a primary reinforcing for certain applications. And in the right situation, I think if my friend Randy posted in his firm Pivot, they did a nice job on the Austonian. That was an ICRI project of the year a couple of years ago, where they made extensive use of FRP bars. But it has to be the right situation. FRP bars or wraps or anything else do not behave like reinforcing steel. They don't have a distinctive yield plateau, and that's problematic if you're dealing with seismic or if you need a certain amount of ductility. So they need, like anything else, they have a place, and they're very, very valuable, but they're not the cure-all for all these problems that we have. So in the right situation, they're a very good repair strategy. In other words, in other things are not appropriate. There's also questions about fire performance that need to be addressed. So you have to understand them and follow the available documents and codes that are being published for them.
Okay. Thank you so much, Keith, for spending time with our audience this afternoon and answering their questions.
Thanks for having me.
For sure. Please visit aciuniversity.com to see our upcoming webinars. And as Keith mentioned earlier, part 2 of this 562 series does start tomorrow at 1 Eastern, We look forward to you joining us then. ACI does also offer our webinars in an on-demand format. That does conclude today's presentation. Please choose to join us for future learning opportunities. We hope you have a wonderful afternoon. Thank you again, Keith.
Thanks, everybody.